Today, we're going to dive into a kind of math that's, well, it's a little different. It's less about complicated equations and way more about powerful common sense. We're going to look at the simple, kind of elegant logic that can solve problems that seem super tricky, starting with a classic riddle. Okay, let's jump right in. Picture this. You have a glass of milk and a glass of coffee. You take a spoonful of coffee, you put it in the milk, maybe give it a little stir, then you take a spoonful of that new mixture and put it back into the coffee. So here's the question. Is there more milk in the coffee glass or more coffee in the milk glass? Go on, take a second and really think about it.
It feels like a trick question, right? It's one of those puzzles that often stumps people, but the solution is surprisingly simple, and it doesn't require any complex calculations at all. This is our first stop on a journey into a more intuitive way of thinking about problems. Let's break this thing down.
Yeah, let's call this the curious coffee conundrum. It's a great test of our intuition, which, can sometimes get tangled up in all the details. But if we just walk through the steps logically, the answer becomes, well, crystal clear. So, here are the two actions. First, a spoonful of pure coffee goes into the milk. Then, a spoonful of that now mixed up liquid goes back into the coffee. The key thing to remember here is that the exact same volume, one single spoonful, is moved each time. All right, here's the insight that just unlocks the whole puzzle. After both of those swaps are done, each glass has the exact same amount of liquid it started with. The total volume in each glass is constant from the beginning to the end. That's our anchor point. So, think about it this way. Any amount of milk that is now missing from the milk glass has to be somewhere, right? It's got to be in the coffee glass. And to keep the total volume in the milk glass the same, that missing milk must have been replaced by an equal amount of coffee. In other words, what is missing from one has simply gone to the other. This means the amount of milk in the coffee is exactly the same as the amount of coffee in the milk. No complicated algebra, no variables, just pure common sense reasoning. It's all about conservation. Pretty neat, huh? All right, you ready for another one? Let's try a different puzzle. This one looks completely different on the surface. We're talking apples, pears, prices, but as we solve it, see if you can spot a very similar kind of logical thinking at play. Okay, here's the situation. In one shopping trip, 4 apples and 2 pears cost you $10. On a second trip, 2 apples and 2 pears cost you $6. Your challenge is to figure out the price of a single pear. Now, before you jump to algebra and start writing out X and Y, let's just look at this with that same common sense lens. What's the constant here? What's the one thing that's the same in both scenarios? That's right, it's the 2 pears. That's our invariant, just like the total volume was in the last puzzle. Let's just lay it out clearly so we can see it. On the left, 4 apples plus 2 pears for $10. On the right, 2 apples plus 2 pears for $6. Seeing them side by side like this really makes the relationship just pop, doesn't it? Okay, so since the 2 pears are in both purchases, the only difference between the $10 bag and the $6 bag has to be the number of apples. The first purchase simply has 2 extra apples. That's it. And what's the difference in price? Well, $10 minus $6 is $4. So those 2 extra apples must be where that $4 difference is coming from. And from there, it's simple. If 2 apples cost $4, then 1 apple has to cost $2. We've just isolated a key piece of information that we can now use to find our final answer. Now we can solve for the pears. Let's take that second purchase. 2 apples and 2 pears for $6. Since we now know 2 apples cost $4, we can just substitute that value right in. $4 plus 2 pears equals $6. And there it is. The 2 pears must cost the remaining $2, which means 1 pear costs a single dollar. We solved it. And again, not with formulas, but just by comparing and simplifying. So, we've just cracked 2 very different-looking puzzles using a strangely similar approach. It's time to pull back the curtain and reveal the powerful, unifying concept that connects them both. The secret is something called mathematical literacy. The OECD defines it as an individual's capacity to reason mathematically to solve problems in real-world contexts. Notice that key word. It's about reasoning, not just calculating or memorizing formulas. In both puzzles, you used what's known as meaning-preserving reasoning. I know, that's a fancy term, but it's a simple idea. You transformed the problem by thinking about replacement in one case and by comparing and subtracting in the other without ever losing the original meaning of what was actually happening.
And this is where it all comes together. Look at this. In both problems, we followed the same fundamental logical steps, even though they looked totally different on the surface. We tracked a quantity, we named an invariant, something that stays constant, we used a transformation to simplify things, and then we interpreted the result. This right here, this is mathematical literacy in action.
But why does this matter beyond these fun little brain teasers? What's the real-world takeaway from all of this? Well, true math literacy isn't about acing a test. It's about developing the flexibility to choose the right way to think about a problem. It's about being able to explain why your logic makes sense. And this is a critical skill for making informed decisions every single day, whether you're looking at your personal budget, a news report, or just your grocery bill. We've just explored a really powerful way of thinking that relies on logic and common sense, not just on formulas. It's a tool that helps you cut through the noise and see the core of a problem. So, the final question is for you. Now that you know the secret to thinking this way, what everyday puzzles are you going to solve?